Hello, this is Shatoki Kaur, and this is a short presentation on quantum oscillation in topological nodal line semimetal. Now, in this presentation, as you can see from the title, these are basically two different topics. So I'll just talk about what is quantum oscillations, and then talk about what are nodal line semimetals and what is topological on that. And then I'll show the connection between the two and the Hamiltonian that I use to discuss such problems and the outcomes I get from there. Okay, so basically the contents is saying the same thing what I just mentioned in a little bit more detail. We'll just go over that as we proceed. So basically, to study the quantum oscillation, the first thing we need to study means we have to start with the motion of electrons in a magnetic field. So we'll study 2D geometry first. So let's consider a magnetic field in a 2D electron gas. So you have a 2D sheet of free electrons, and then there is a magnetic field perpendicular to the plane. So what happens? Let's just follow with as I'm going. Don't worry about so many things here. So we'll first take a look at the force. The force is the Lorentz force. So if you have a velocity, the electron has a velocity, then it will have a Lorentz force, and then see the direction of the Lorentz force. It's perpendicular to both the velocity as well as the magnetic field. So it will turn the electron, then ultimately it will give a circular motion. That's called a cyclotron motion. And then if you go to the equations, you will see this is mv square over r, which is the centripetal force. You equate that to your Lorentz force, and then from there you can see the angular frequency of such rotation will be given by omega c equals eb over m. This omega c is called the cyclotron frequency. And picture wise, you can take a look at this cartoon. It's a 2D sheet of electrons, and then as the magnetic field is applied perpendicular to the plane, the individual electrons are doing these cyclotron loops. Now these two things, we'll just come back to that later on. Now this is the main picture. Now if we just go into a little deeper, if you go to the momentum space, the k space, to see what is happening, then you will see there's something called Landau quantization that occurs. First of all, at b equals to 0, the Hamiltonian is just the kinetic energy. So h equals to p square over 2m, and its wave function is like plane wave functions, e to the power exponential like k dot r, and this is the energy eigenvalues. And then if you look at the k space, how the k space points looks like, so if you have a finite geometry with dimension, let's say L and L both on the kx and k will be equally distributed, and the distance between the consecutive two k points will be 2 pi over L. We know that from our solid state knowledge. And these concentric circles here denote the equi-energy lines, incompatible with this expression of the energy. Now, if the magnetic field is applied perpendicular to the plane, then there is something called Peierls substitution, or the generalized momentum that we have to consider, by which P changes to P minus E times A, where A is the magnetic vector potential and E the charge. So now if you plug that in the Hamiltonian and just do follow some steps, you will see ultimately you will get a Hamiltonian which looks like that. Py square over 2m plus half m omega c square times y minus y naught whole square. This is the Hamiltonian of a simple harmonic oscillator. So its energy will be given as E equals n plus half h cross omega c. This n are integers, and these are called, in this case, the Landau level index. So you can see there's a quantization that takes place as magnetic field is applied to the system. Now here, there is another thing to notice is that this y naught is actually given by px over eb, where px is the component of the momentum along the x direction. So because that's not a single value, it can have many values for this px. So you can have many values for y naught, but for each one of them, the energy will still be the same. So you can see there's a huge degeneracy attached to every Landau level in this problem. And then if you go to the k space, how you can see this thing? In the k space, there is some complete rearrangement of the allowed k points. Now we can have these concentric circles, and each circle corresponds to one Landau level, n equals to 0, 1, 2, 3, something like that. and then all the k vectors, allowed k vectors, will always fall along the circumference of these circles. So that's how they are distributed, and the number of them should be the same, because this is actually giving me the degeneracy coming from these different values of px. So that is the picture. Now if we go to the third 3-dimension, you will see that cyclotron loop, the 2D cyclotron loop of the electrons, can now advance forward in the third direction, in the magnetic field direction, and then you will get a helical motion. But if you go to the momentum space, the k space, you have these semi-classical equations of motions in the k space, and then that indicates that even now in the k space, the electronic motion will be given by this cyclotron loops, 2D cyclotron loops. But the difference here is that those cyclotron loops can be in different plane, different parallel plane, designated by constant values of kz, where z is the direction of the magnetic field. And then you can see that also from here, the Hamiltonian formulation, as you give the magnetic field. Now in the energy spectrum, you get other than this Landau level quantization, you get this extra term, h cross square kz square over 12, and because of that you get this kind of thing. So this tube kind of thing, this is called a Landau tube, which corresponds to one particular value of n. So in the Landau tube, all these electrons here, they all move along its surfaces and then in plane parallel to the kz direction, but they not necessarily have the same energy. For example, this the energy of this one, where kz equals to 0, is least compared to the other cyclotron loops where kz has some non-zero values. And then we have shown this sphere here. This is the Fermi sphere. So the portion of the Landau tube which is inside this Fermi sphere are all occupied, because we know that's the picture at 0 temperature. And if we go beyond, there will be states, but that will be unoccupied. You can always also plot the dispersions like that. For different n values, you will get these parabolas. And here, this is actually kz. I forgot to write that down. So that is the picture. Now, let's take a look at this picture first. It is showing that because there are many different n values are possible, and for different n values, you will have different Landau tubes, and they have different widths, because the width depends on the value of n. So you can imagine a picture like that. Within the Fermi sphere, you can have that many numbers of Landau tubes lying like that. Now you change the magnetic field, what happens? From there, I can get quantum oscillations. If you change the magnetic field, the width of the Landau tubes changes. It increases actually with magnetic field increase. And you can see from this cartoon that as I'm increasing the magnetic field for a particular Landau tube, its dimension is increasing. It's getting more and more fat. And at one point of time, its width can be more than the width of the Fermi sphere, and it will go outside the Fermi sphere. And at that point, there will be no occupied states available at that Landau tube. Now take a look at these two pictures. So here, this is a Landau tube, and this is showing an energy shell corresponding to energy between E and E plus D. Now, if you want to find what are the electrons within this Landau tube that have that much of energy between E and E plus D, we can see that that will be given by the electrons that are in this shaded region. So if you calculate the density of states from there, that will be proportional to the volume of this shaded region. So this is a general picture, but it can so happen the width of, or the area cross section of this Landau tube becomes same as the largest area cross section of this energy shell, like in this one. And in that case, you can clearly see the shaded region is not two distinct shaded region, but one huge shaded region in the center, in the middle, and whose volume is much more. So in this kind of scenario, you can see huge jump in the density of states value. So this happens if you keep on changing the magnetic field, or if you keep on changing the energy. And this area of cross section, which is the where this is actually maximum, or it could have been a minimum also for this energy shell. This is called the extremal area of cross section. So the thing is that whenever the Landau tube width becomes Landau tube cross section becomes same as the extremal area cross section corresponding to the energy shell that you are interested in, we see a peak. And then you can see these are the typical plots of the incident states you can get as you vary the energy and keep your magnetic field fixed. Then you can get a plot like that. So it shoots up to a very high value and then again falls, just like a 1D density of states, and then again shoots up when the available next value comes. And this is happening because as you increasing the energy, different Landau tubes are there. So for different Landau tubes, you can have this kind of situations, and for each one of them, you are getting one of such peaks. So this is the picture. Now this is showing this the variation is showing with respect to energy. You could have kept the energy fixed and then see the variation with magnetic field also. You know that if you change the magnetic field, the gap between these two will also increase because the gap is actually omega c, and omega c depends on p. So in that case also, if we fix a E and then see the variation of the density of states with magnetic field, we will see a oscillation, and this oscillation is called the quantum oscillation. And then it's very nice. We can just, if you just study closely, we can see that it has some constant periodicity if we plot with inverse of p. So remember that this oscillation that we are talking about, this is not any oscillations with respect to time or space coordinate. This is oscillation with respect to magnetic field. And then we will see that it has a constant period if we just plot it not with b but with 1 by p. And this is actually showing here. So you can do the maths. You can get the area of this Landau tube cross sections, which will be given by this thing, and you can also get that from more general Onsager relation, which is this expression. And then for a particular value of energy or chemical potential, you have a particular value of area of cross section for the Fermi surface. This is given by SE, and whenever Landau tube area cross section becomes same as that, we get this density of state peak. So we want to locate, we want to see where this density of state peaks comes as we keep on increasing the magnetic field. And then you can see two consecutive Landau tubes as it passes through the Landau passes through the Fermi surface. At one point of time, their area of cross section becomes the extremal area of cross section, and then if you can compare that, ultimately you will see the change in inverse of magnetic field as you go from, let's say, nth level to the n plus 1th level. And in both the cases, you see the density of states peak, that is in fact a constant number, which is given by this thing. And in the picture, you can see it more clearly. This is magnetic resistance is plotted with magnetic field, and then we see this quantum oscillations. So with magnetic field, the oscillations is coming. But if you plot the same thing with not b but rather 1 by b, 1 by Tesla means 1 by b, you will see that the periodicity of these oscillations can be seen to be constant. So here this is not constant, this is growing more and more, the periodicity, but in this case there's a constant periodicity which is at par with these calculations. So that is very simply saying what quantum oscillations is, and that's what you see in the 3D electron layers. Okay, so now we'll come to the nodal line semimetals, but in the nodal line semimetals, we can just spare 1 minute for this introductory slide. So this is showing the typical electronic band diagrams. If there is no gap between conduction band and valence band, we have metal, and if there is gap, then depending on the size of the gap, we can have a semiconductor or insulator. But things can happen that for in the Brillouin zone, for some of the discrete k values, you can see gapless spectrum. So at those k values, there is no gap between conduction band and valence band, but for the other k values, there are gaps. These kind of situations are called semimetals. So they are in between of these metals and insulators, and you can tune it to either way by various mechanisms. And because there is only a few available states for which gaplessness is there, and then electron can conduct. This is not very interesting in that respect. It cannot be it cannot have enough of conductivity. But turns out if this crossing is linear, not like that it's shown here. If the crossing is linear, then things changes dramatically, because for linear crossing you'll get effective mass to be zero, effective mass of electron to be zero, and at the crossing point, and then it gives huge mobility to the particles, to the electrons, and then you can see many dramatic effects, and that's what we're actually aiming for going to. Now, when that happens, that there is a linear crossing, we have to actually use Dirac equation, because we know in the for the relativistic particles we use this Dirac equation where the particles has a constant velocity of speed of light c. Here we don't have a speed of light, but we have a constant speed which is given by the slope of these straight lines in the dispersion diagram, which can be given as VF, which is the Fermi velocity of the electrons. And then because there is at least two bands we have to consider, so the Hamiltonian we consider are at least 2 by 2 matrices, and that can be simply given by this kind of Dirac Hamiltonian. Sigma is called some pseudo spin vector. It can be because of orbital degrees of freedom. It can also be because of spin degrees of freedom, if the spin is there in the problem, and this p is the momentum. Now this picture that is shown here, that this is Dirac point and this is conduction band, this is valence band. This is actually for 2D geometry, just like graphene. So it's a single sheet of monolayer of the graphite allotrope of carbon, and there when you go to the K space and see the dispersions, we will see things like that, and these are named as Dirac points and Dirac cones, these ones like that. But if you come to the 3 dimension, the similar thing you can find, though very rare, but you can find recently it has been found in many compounds. So there, whenever the bulk dispersion relation show this point touching of the conduction band of valence band in a linear fashion, and those are called the wild semimetals, and those points where they touch, they are called wild point. But more common to this kind of scenario will be if the touching is not along some particular discrete points, but along some closed line in the Brillouin zone. And that's where this is the typical cartoon for that. And that's what is called the nodal line semimetal. And this is what we are going to discuss in the rest of the talk. So it's a lot of things are there. Let me just simplify and then say a few things of this. So this is my typical nodal line semimetal. So they're crossing linearly the two bands, and then linear crossing along a close line in the Brillouin zone. Now the question is why it does that. Now take a look at this picture. This is a picture we all know in the free electron theory. We have seen these pictures. So it's basically showing that two bands and a point where they comes very close to each other, but they don't touch because they hybridize, and then we can deal with this problem using degenerate perturbation theory, and then see how the two bands which are about to cross but they don't cross, and then open a gap between them. This is called band repulsion. But this cannot happen if there is some additional symmetry attached to these bands, and that symmetry prevents from opening up these gaps. There can be many kind of symmetries, like there can be mirror reflection symmetry, inversion symmetry, time reversal symmetry, etc. And because of that, for example, in this case, let's say this conduction band and valence band correspond to different eigenvalues of the symmetry operators. In that case, hybridization cannot occur. So this gaplessness is protected. It cannot be just like that. You cannot just open a gap there. So these are the nodal line semimetals, and the examples of some will be given like that: ZR-SIA, ZR-SIAC, ZR-SIT, etc. Now these things are called topological. This is very vast topic. Just go very simple way to understand what this means. So basically, what it means that this nodal ring that we have talked about, where the conduction band and valence band touches, You cannot deform the system and squeeze it out and then just throw out this. You can just make this thing vanish suddenly by some deformation. This is there. You can make it small or big, but you cannot completely kick it out. That is the topological robustness it has. And then what is the indication of that? Quam means physical quantity wise. If you can imagine a electronic loop like that, which rings through, which goes through this nodal loop, and then you calculate something, you have some closed line integral. So this is some mathematical construct. This is Berry connection, Berry curvature, and Berry phase given like that, where this u, as you can see, this u is the electronic wave function. We don't need to go into many details on that, but just to see that what is actually being done is that this kind of things we can calculate in the momentum space, and this is called the Berry phase. And then if you calculate the Berry phase along this kind of closed loop of electrons, you can see we get some non-zero values. That non-zero values is an indication of that the system has some non-trivial topology. If it would be a zero value, then we would say that system doesn't have any non-trivial topology. For example, if my loop was not like that, a different loop like this, which does not ring through the nodal loop, then if you calculate the Berry phase, you will get a zero. So this Berry phase is very special in determining whether the system is topological or not. And the topological invariant in this kind of systems are called Chern number. This Chern number is actually very directly related to this Berry phases. So you have to calculate, you have to sum it up for all the occupied bands. Okay, now we'll just spare also one more slide for topology, just in the next slide. Okay. So now this is the thing, this thing we get in the bulk spectrum. But if you want to experimentally determine the topological robustness of these systems, generally we use angle reserved photon emission spectroscopy. But these things are more concerned with the surface effects. So we have to see the effect of the topology in the surfaces also. But this kind of systems, the surface states, like the states that are localized at the surface, does not show always very much topologically protected behavior. So it's very difficult to sometimes determine whether the topological robustness this kind of system has. But in that case, if you can do quantum oscillation measurements, and then from there you can calculate the Berry phases very easily. And if you see you get some non-zero value, you can tell that this system has some non-trivial topology. So that is the connection for quantum oscillations in this nodal and semimetals systems. So we'll just go over that, but one slide for the topology. So topology is a mathematical concept actually. If you can imagine these shapes, this sphere, it doesn't have any hole inside it. This is torus or donut. It has single hole in it. You can have a double torus, or you can have a triple torus like a pretzel, which has 3 holes in it. So all these different shapes are in different topological classes. And these topological classes, these topological states are very robust, because you cannot just deform one of these shapes and make it to the other one. You have to change the number of holes. But the number of holes is a very robust thing. You cannot just by simply local deformation change that. And then they are given by this number genus, which gives the number of holes. So for sphere is genus 0, for torus is genus 1, like that. So this is the mathematical concept of topology, to saying it very, very simply. And thanks to these professors, Professor Thouless, Professor Halden, and Foster Leach, who worked on topology in physics and got 2016 Nobel Prize. And they actually found out the connection that they said that this topological robustness can be found out in physical systems also. For example, let's take this cartoon again, which we have seen before also. This is a 2D topological insulator. So it's a finite geometry. With these two sides are not shown, that I couldn't find in the cartoon I got from the internet. So here, see, because of the magnetic field, which is perpendicular direction, we get this circular motion for the inside electrons, and that's why the electrons doesn't move forward and doesn't give any current. So in this region, there is no current passing, and this is actually an insulator. But then if you look at these edges, here the electrons cannot complete its cyclotron orbit because the edge comes in the way. So what it can do, it just again try to make another loop, and then this way keep on moving forward and forward and forward. So these are called skipping orbits. Because of the skipping orbits, the right moving and left moving, ultimately current flows along the edges. This current is a very topologically robust thing. You cannot just deform the system and then change this current. So this is the connection of this topology that we knew from mathematics point of view, and to this physical system. So you can see here also in the physical systems also you can have something like topologically robust, very robust, and you cannot just change it by some local deformation. And then if you want to calculate it, there are some ways. You have to go to the momentum space and then do some mathematical construct like that. You have to know what is, you have to get the Berry connection, Berry curvature, and the Berry phases. And then from there, you can calculate the Chern number and then see whether that is non-zero or zero. If it is non-zero, then that indicates that it has some topological non-triviality. So that much we should know as a beginner for now to keep going with this topic. So then in our system, so this is a simple Hamiltonian for a nodal line semimetals. So don't worry about all the details. Just see that this is a 2x2 matrix because of this sigma Pauli matrices, and these are giving orbital degrees of freedom coming from this conduction band and valence band. And if you get the energy eigenvalues by diagonalizing it, you get an expression like that. This plus minus are for conduction and valence band. And from there you can see this epsilon, the energy becomes zero where the conduction and valence band touches, and the locus of that would imply pz equals 0 and p perpendicular square equals 2m m star, which is a circle in the pxpy plane. So that's the nodal circle. So you can see this Hamilton is actually showing a nodal line, demonstrating a nodal line semimetal. Now if you plug, if you just put a magnetic field in the perpendicular direction, in the z direction, again we have to do this pure substitution, Landau quantization occurs, and you can see in the transformed Hamiltonian you have these n indexes, which is the Landau level indexes, and these are the expression for energies. Now from there you can find the Fermi surfaces. The Fermi surfaces are not unlike the previous case of electron gas. We were having these spheres because it was isotropic, no potential was there. But for this particular Hamiltonian, we will get Fermi surfaces like that for energy 0. There is no surface, it's only one ring that falls on top of the nodal loop. But if you go to higher energies, you will get this torus shaped Fermi surfaces. And then if you go and within that Fermi surface, you will have actually this nodal loop sitting. And then if you keep on increasing your energy, you will see the size of that torus grow, and the inside hole becomes smaller and smaller, and at one point of time there is no hole anymore, and then you have a drum shaped Fermi surface. So clearly this is a change in topology. So now let's take a look at this low energy Fermi surface, which looks like a tire. It's a torus like that. So this dashed circle I have just shown to show that inside that we have this nodal loop sitting in the momentum space. This is a momentum space we are discussing, right? So now we have to understand quantum oscillations for this kind of systems. Now for quantum oscillations, we again remember what we are trying to achieve. We are trying to understand one oscillations which occurs with magnetic field variation. Now, like in any oscillations, if you want to find the period, we have to fix at one particular phase and then see when next time that phase comes back again. And then from there, I can calculate the period. So this is done here also. So that particular phase that we want to zero in is the one where this density of state shows the peak. And then wherever the density of state shows the peak, we know at that moment the Fermi surface cross section becomes extremal. Now, in this case, we have to find where the Fermi surface becomes the area of cross section becomes extremal. Now, this area of cross sections are always perpendicular to the direction of the magnetic field. So, if my magnetic field is in the z direction, so the extremal surfaces will be correspond to kz equals 0, or k perpendicular equals to 0 more precisely. Perpendicular means component of k parallel to magnetic field direction. So these are the two yellow circles you can see. Those indicate the two extremal surfaces. So in this case, we have two extremal surfaces, unlike in the electron gas problem where we had only single extremal surface. This is if my magnetic field is along the z direction. Now, if my magnetic field is along the x direction, you will see now we have to consider the px equals to 0 plane, where I can which we have to consider, and then the extremal surfaces occur at px equal to 0, and these are shown like these two cyan or blue colored circles. So again, in this case also we'll have two external surfaces. Now see the difference. When we have these yellow circles and electron goes along these circles, then that pathway doesn't ring through or doesn't cut through the nodal loop which is sitting here. So that's why it gives a zero Berry phase, and then this magnetic oscillation is trivial. But on the other hand, when magnetic field is along the x direction and when an electron goes along these circles, these circular loops, it rings through this black nodal loop sitting over here. So in this case, as we have said before, we will get a non-zero Berry phase. So for this case, we can have topological oscillation. So this is the difference between a magnetic field along z direction and magnetic field along x direction. In one case, I get trivial oscillations. In the other case, we get non-trivial oscillations if my energy is small. If my Fermi surface is of this drum shape, then we will not get topologically robust oscillations. Okay, so this is the thing. So so what do we do? We, for magnetic field perpendicular to the nodal plane, which is the z direction, to study the quantum oscillations, we put kz equals to 0. So as kz equals to 0 is put here, we come back to this simplified expression of dispersion, and then you can see we can plot it with magnetic field. For each n values, we have two sets of dispersion lines, and for different n values, we have again another sets of dispersion lines. Now, if you consider one particular energy or chemical potential, let's say mu1 you consider, then you can see for each n value at that mu1 level, you can have two magnetic field values. These are two magnetic field values corresponding to which you can have two Landau tubes whose cross section is the same as this extremal cross section given by this yellow circles. And then if you go to the different n value, you will again get another two sets of b values like you got in the previous case. Now, if we collect all these b values corresponding to coming from one particular branch, either plus or minus, and plot that in a 1 by b versus n diagram, this is called a Landau fan diagram. You see they are aligned along a line, so they are linear plots, and that can be seen from this Onsager relations also, which can be written in this fashion, that they are in fact straight lines. If you plot 1 by b versus n, you get a straight line, and then that is not only that is true if you consider both plus or minus branches of this dispersion. Now, wherever this lines touches this n-axis, means whenever this 1 by b is 0 or theoretically b is infinite, the value of n corresponding to that will be minus gamma. So if we have these plots from this extension and then from this intercept, we can calculate the value. We can obtain the value of this gamma. This gamma, remember, this gamma was a factor was in the Onsager relation here. Onsager relation here. This is actually in most cases it's half, but not always. And this gamma is actually related to the Berry phase in this fashion, gamma B. So here you can see this gamma value is actually half for when my magnetic field is in the Z direction. And then you can, from there, you can actually calculate the gamma B, and then that will be 0. So that is, we can see that very easily we can find out from the Landau Venn diagrams that my Berry phase will be 0 and the magnetic oscillations should be trivial magnetic oscillations. Now, if we look at the other case, when my magnetic field is parallel to the x direction in the nodal plane, then the situation is a little bit more nasty because it has less symmetry. Because before there are xy in the direction, the xy direction, there is completely symmetric. Now I break that symmetry by putting a magnetic field in the x direction. So basically, we cannot just analytically handle this problem. Like we can do the pure substitution, but we cannot proceed further to get a very nice Landau quantized form of the Hamiltonian. So, but we can solve this problem numerically. You can use exact diagonalization and then get the dispersion plot, and then that can show me that the external surfaces can occur at px equals to 0. So here again we put px equals to 0. Now if you put px equals to 0, you can see, you can again start considering the magnetic field equals to 0 situation, and then you will see this Hamiltonian now will indicate 2 direct points at this two positions in the momentum space. You can see it from this picture also. So this was my nodal loop, and this is my px equals to 0 plane. So this plane cuts this nodal loop at 2 points, and these are the 2 points where I can get some get 2 direct points, and the Hamiltonian for the 2D Hamiltonian for px equals to 0 will be some anisotropic Dirac Hamiltonian about these 2 direct points when there is no magnetic field. And then if you put your magnetic field, things from there changes, and then ultimately you can ultimately you can numerically solve the problem, and you can get spectra like that. But if you want to try, if you want to understand what is going on, you can just go to the very low energy limit, and then you can get some semi-classical equation, semi-classical form of the energies, and you will see that they take a form like that. So my energy, when for low energies, the dispersion will look like some constant times square root of n, where n is the integer. So now we can call this n the Landau index, Landau level index for this problem, and they are all doubly degenerate. And you can imagine why is that so, because we had 2 direct points. So each of about the direct points, if you have some linear harmonic oscillator like spectra, and they have similar energies, so from each one of them you get one set of spectra, so ultimately you'll get double degeneracy. So it's just like hand waving way I'm telling you all these things. If you follow the mathematics, you'll see that they will be actually doubly degenerate. So the thing is that this is, let's say, this energy line I'm considering, this is doubly degenerate, and as you keep on increasing your energy at one point of time, rather, as if you keep on increasing your magnetic field at one point of time, the energy increases, and then at one point of time they split up. The double degeneracy is no more there, and then you get 2 branches coming out from this this branch which was degenerate before. So this is where this happens. This is actually a transition, topological transition occurring here, and then also this is where my Fermi surface is changing from this torus Fermi surface to a drum Fermi surface. Okay, and then if you calculate the Berry phases, if you do the Landau Venn diagrams just like before, and then get the intercepts, and then they will indicate Berry phases which is non-zero if you are at very small energies, but it will be 0 if you are large energies, which is above the position where this breaking of the degeneracy occurs. You can see also this picture. So at small energy, you have this torus-shaped Fermi surface. At large energy, you have this drum-shaped Fermi surface. And then you can take a look at the cyclotron orbits of the electrons in these two cases. So you can have these two separate cyclotron orbits in this case, and the direct points we talked about before will lie inside these two cyclotron orbits, and each one of them will give me some Berry phases, plus pi and minus pi. So overall, so we get non-trivial topology in this situation. But for large energy, the cyclotron loop is not like this small loops, so it will cover both the direct points. So the overall Berry phase coming from line integral of along these lines will be plus pi minus pi equals 0. So there is a 0 Berry phase, and this thing indicates a trivial oscillation. So that is the difference. That is the thing basically we pretty much wanted to say, and already I have said everything. So just very briefly, I'll just summarize. So we're talking about nodal line semimetal under a strong magnetic field. We talked about the spectral and topological responses, and as the magnetic field strength is varied, we consider two cases. One is magnetic field perpendicular to the nodal ring, another is magnetic field parallel to the nodal ring. For perpendicular to the nodal ring, you can have trivial magnetic oscillations. For parallel to the magnetic field, you can have non-trivial magnetic oscillations if my energy is low. A further thing we can mention here that if we have AC alternating variation of the magnetic field in the region of interest that we are discussing so far, we can have these Landau states which are situated very close by in the momentum space. We can actually have transfer of electrons from one band to the other band, like a Landau-Zener-like transformation. So we can so that's also another nice thing we can have in this situation, in these problems, if we have a alternating magnetic field, and that can also change the conduction picture of this problem. But that's just a future work we can also do. Means that some of such work is done here, but many more from there we can do. So this is something we can do from here. So that is pretty much all. Thanks for listening. And this is actually work. This is funded by DST ACRP under this grant number. And I also thank Mr. Anupam Shah, who is actually working as a GRF under this same project. So thank you so much. Thank you very much for listening.